All right, let's do a walkthrough of week 6 homework. This has been kind of the same as we did for week 5, and then we're going to do again for week 7 until we get kind of the hang of reading in a data file, manipulating the data, cleaning it, analyzing it, and doing a curve fit. So that's what we want to do here. So we're going to go ahead and import our various packages that we're going to need, as we've done before. And then we're going to go ahead and read in our data file. So I've got the path here to the data file on my machine. Our data file is week 6 data. It's in an Excel file. And we'll go ahead and we'll combine those two paths together into one string. And we'll go ahead and read in the data using Pandas, read Excel. And so this is our standard input. And we need the from path library import path statement for this to work. All right, so let's go ahead and do that. We talked about this before, but there's many ways of defining the path. Doing it this way with this path command hopefully allows this to be a little more robust and work on both the PC and the Mac. All right, so we'll go ahead and we'll read the data in, and we can see that our data has some columns here that don't have any data in it. So we want to get rid of those. And after we do that, we want to maybe clean up some of these rows that are missing data. So to clean the data, first thing we're going to do is go ahead and make a copy of what we read in, which is what I called raw. So I'm going to just call that data now. I'm going to go ahead and make a copy so that I'm not affecting the original data. And then I have a couple of choices. I could take the data and I could drop NA, right, where there's no values, the NA ends, and I could apply it to axis 1, which is columns, and I could use the HAL equals all option. And so this says that any column that contains all NaNs, drop them. So in this case, that would be only these two columns. There's also the option any. If it's any, that would say any column that has at least one would get dropped. And we don't want to do that because here's an NaN in this column, so that would drop that one. Here's one in this column, so it would drop that one. So everything would get dropped. So you got to be careful when you use this. Okay. And then if we want to do rows, we're going to use axis equals 0. So we'll do that in a minute. So I could do that. I could also use the drop command directly and just name the columns that I want to drop and tell it we're dropping by columns. Or I could just take a slice of the columns I want rather than dropping columns. And so I'm going to just do it that way this time, but any of those would work. So I'm going to go ahead and take my data frame, right, and I'm going to use my LOC here from Pandas, and I'm going to say colon, which means take all rows, because this is rows, and then columns is the format here using .loc. And so colon just means all rows, and then I'm going to take, and I can just give it a list of columns to take. And so I'm going to go ahead and take times seconds and crystallization fraction. So I do that, and then this is what we get. All right, so that looks good. And now I got to go ahead and deal with these NaN values and this one here, which is missing altogether, and this one. So first thing, before I start doing that, I want to just check now the information on this data frame and see what I've got. So I go ahead and run my data info. And there's a few things to notice. There's 200 entries total. Okay, and it also says it right here. There's 200 rows, right, by 2 columns. So there's goes to index 199 because we start off with index 0. So that's 200. And then if I look at my 2 columns, time and crystallization fraction, it says time has 199 non-null values, and this one here has 198 non-null values. So if I look at my columns, crystallization fraction, here are the actual 2 values that are null, and then everything else is non-null. So it gives me 198. And then over on this one, it says I have 199 null values. Okay, but I've got this one and I have this one. So this one here, although it's not data, doesn't show up as a null value, right? The NaNs are null values. So this is a string in the midst of all these numerical values. And that's why when I look at the data type here, you can see that it says object, because this is a mixed column. It's got a string in it, it's got numerical values. So I want to fix that by converting this column to data only, which is float. And I want to tell it to coerce that conversion, which means if it runs into an error where there's something that it can't convert numerically, like this string, then it will change this to an NaN, okay, rather than just throwing an error. And so that's what we're going to do. So we're going to use the Pandas to numeric, and I'm going to apply that to this data time seconds column, and I'm going to tell it if there's errors, coerce it. In other words, turn it to NaN. So I'll go ahead and run that and take a look at the info. After I do that, I can see now I've got a float. All right, so that looks good. Let's go ahead and take a look at the data, see what it is. And you can see now that the dash that I had in there, string, is now listed as a null value. All right, so now I can go ahead and get rid of rows that have a null value. And in this case, I want to get rid of any row that has at least one. So I don't need this set of data. I'm going to get rid of this one and get rid of this one. So I'm going to use the axis 0, which means row, and the how any. So as long as it has at least one in the row, it will get rid of it. So these three data points will go away. So I'll go ahead and do that, drop them, and then here's now my data. And if I was to go ahead and do data info now, go ahead and do that. You can see everything looks nice. There's 197 entries and 197 non-null values. So that means I don't have any nulls floating around. I've got the equal number of entries as I do non-null values, and they're both numerical. So that means I have all numerical values. So I'm happy. All right, so let's go ahead and we'll start analyzing the data now. So one of the things I needed in this problem was to add a column with the time in hours rather than seconds. So I'm going to just go ahead and add that column in. And that column is going to be calculated by taking the second column and divide it by 3600. And this is just a warning related to working with copies or the original set of data. You can ignore it. So it's a little complicated sometimes why it's throwing this, especially when we're using this format, which should be fine. But let's just not worry about this one. It's not an error, it's just a warning. But I can see when I print my data out that it did what I wanted it to do. My data frame data has been updated to include this new column, and so that's fine. All right, so now I can go ahead and plot it. I'm going to plot the hours column versus the crystallization fraction. And there it is. And now what I'd like to do is fit it. So in 2044, we learned about crystallization versus time. And we did this in the phase transformations chapter. And one of the things we found is that this crystallization fraction follows what's called an Avromi curve. Okay, so this crystallization fraction is going to go from 0 to 1, right? And then we've got our time axis here in hours. And they always have this kind of S-shaped curve, and it's defined by this equation here, the Avromi equation. The Avromi equation has two fitting parameters. It has this value k, which is the coefficient of our time variable, and it's got n, which is the power on our time variable. Okay, n's usually somewhere in the 2 to 3 range. K just depends on our time. In this case, that's going to end up being something like 10 to the minus 5 or so. So I'm going to define my function that I want to fit using the curve fit command. And the important thing to remember, when I call the curve fit command and I give it my function here, and I give it the data that it's going to fit, there's nothing in this that tells of the Avromi curve that tells it where in this function this x values need to go, the time values. And so that's because the curve fit command assumes that the first parameter or first value that goes into this function is your variable, your time in this case. So when I define it, that means I've got to make sure that my variable, my independent variable here, is included first in my function definition. And then after that, we have all of our parameters. So it's these parameters, k and n, that are actually fit, right? So this curve fit will find values for these two that make this function fit the S shape. Okay, so again, the important thing is make sure that your variable is first. Okay, so when we did the linear fit, x came here. Right, on this one we've got an equation in time, so t needs to come here. All right, so once I've got that, then I can go ahead and call my curve fit, pass my function, give it my x data, and then give it my y data. Right? That's the x and y values that's going to try and fit to. And that's all there is to the curve fit. All right, the curve fit outputs it returns two values. And so since it returns two values, I need to give it two variables in which to store those two values. And these can be anything you want to call them. I've called them something different here just to remind you that there was nothing special about what I called them last time. So I'm going to call the first one, because the first one that comes out is always the solution of the fit to k and n in this case. So I'm going to call that my fitted parameters, fitted params. Okay, this is the one I really want. And then the next one is a statistics matrix that tells you about the goodness of fit. And we're not going to play with that one, but I do need to give it a name here just so it has a place to store it. Okay, otherwise we're not going to mess with it here. All right, so I'm going to do the fit, and then I'm going to go ahead and show the fitted parameters. So let's do that. So here's my fitted params. It's simply an array of two values, and it has two values because my function here only had two parameters. So if this was like a polynomial where maybe I had 5 or 6 parameters like coefficients I was fitting, then this would have 5 or 6 values in it in the order that I'm given in my definition. Okay, so that's my k and that's my n. All right, so let's see how this fits. So we're going to go ahead and plot our data again. So this is just plotting data, black, small points. And I gave it a label. I did this because I'm going to go ahead and put a legend on here just to show you how you can use legends, just label. And then I'm going to take now and plot. Again, I'm going to use the time values for my data, and then I'm going to feed each of those time values into this Avromi equation. So I'm going to feed them in here to t. And I'm going to give it the k and n values for the fit. And so this will give me out now the crystallization fractions. So let me go ahead and do that. So here's my Avromi function. Here is the time values that are going to go in, and for each one of these time values, it's going to calculate out a crystallization fraction. It's going to calculate and return this function. And then I need to give it k and n. So the easy way to do that is to use this star function. And so fitted params is what contains my two values. And so by using the star, what it's going to do is it's going to input these two numbers and remove the brackets around this in this array here. So it's just going to put the two numbers in bare like I need in the way this is defined. Okay, so it's just a short way. The longer way would be to copy these numbers by hand and put them in here with commas, or I could call, perhaps I could put them in here instead of copying by hand. I could say fitted params, and I could grab the first value, for example, and then I could use a 1 here to find the second value, and I could put those in here with separated by commas. Okay, but this makes it nice and easy, and if I end up with 5 fitting parameters, this will still work. It'll just put all 5 in for me. So we're going to do that. This is, again, it's a start expression. I'm going to make it a red line, and I'm going to label it fit. And I give my axis some labels, and I'll go ahead and do that. And you can see it's a pretty good fit. It falls on our data set. And so now we have some information about the crystallization kinetics of this problem, as I now have the k and n values for the Avromi equation. All right, another word about the fit. This function here is actually fairly sensitive when it's being fit. So, you know, this is on hours, but if this scale suddenly was seconds, it may have quite a difficult time fitting it. And so when that is the case, you can tell the curve fit function some initial values to start with. So I could, instead of just giving it the data and hoping for the best, if I get an error or it comes out with a fit that's really bad, then what I can do is put in this P0. So this is the initial values, if you want 0 here for the parameters. This has to stay in this form. This is defined by curve fit. And then I give it a list of starting values to use in the same order again as my parameters in my definition. So k first and then n. And so here I could guess and tell it, go ahead and start with 10 to the minus 4, and go ahead and start with 2. And that would help the fitting procedure if it wasn't giving me an answer out. And so this is a way, again, of including initial values when you have trouble in your fitting function. All right, so let's see, where are we? So we plotted it, we got a nice fit. And then the last part of the problem was just to find what the crystallization fraction was for 125 hours. So on this plot, we can see that looks like it's over 0.8. It's above that, somewhere in here. To get that, all I got to do is take my red curve here, which is my Avromi, with the fitted parameters. And this first value, remember, is time. Well, rather than giving it all these various points to put into the function to calculate the whole curve, I just give it 1. Just pass 125 hours, and it'll kick me out my answer here. So 0.853. And that's all. Let's look at the start expression just for a second. So let's say we had a test function like this. So my x, and I've got a, b, c, d, right? Just a polynomial. And if I wanted to use it, then I could go ahead and say, okay, for x equals 1, a equals 4 here, b equals 3, c equals 6, d equals 7. I run my function, I get the answer of 20. Well, let's say, like we had before, I had some kind of a list that had the a, b, c, d in it, like here, a list 4, 3, 6, 7. So it'd be nice, right, if I could just simply do something like this and be done. Now, the problem with writing it like this, so this is going to give me an error. You can see the error here, is that this here is actually a list, so it includes these brackets. And so if I write it like this is the same as writing this test function out in this format here. Okay, and that's not the format we asked for, right? We've got 1, 2, 3, 4, 5 parameters that this is looking for. Here, I've given it 1 and then 2. The second parameter is a list of values. So it only sees 2 parameters, and it's going to give you an error. It says missing 3 required positional arguments. What's missing? B, C, and D. Okay, so this isn't the format. And that's where the start expression comes in. So the star on this gets rid of the brackets when it's put into the function. And so I just put it in like this. 1, comma, star, A list. And it'll just stick those numbers in without the bracket, the list bracket. So this means exactly this as if we typed it out by hand, and I run it and I get 20. And so that's what the start expression actually does. Okay, so and that can be used in, you know, at any combination you want. Like I could have test function, and I'm going to keep the same numbers here, right? Let's say that I have a list that's got 1, 4, 3 in it, and then I'm going to manually put in 6, 7. Okay. So if our idea of how this works is true, then this star on acting on this list should just put in 1, 4, 3. It would remove the list brackets, and then 6, 7. And that's what I have here, 1, 4, 3, 6, 7. So let's see. Yep, that works. So again, that's just how this start expression, very handy. All right, I think that's it for now.